Hello, this is a lecture on quantum mechanics for my SEM 4 students, and I would be dealing today with few of the problems, and this I have came to know recently from one of my students because I had been uploading the content of the course, and I was not actually aware of the problems of my student. Recently one of my student gave me 3 problems, and from there I came to know that really we need to deal with certain problems in quantum mechanics. So let us begin with few of the problems regarding the Heisenberg uncertainty principle in this particular lecture. So the first problem deals with the calculation of the de Broglie wavelength of an electron having a kinetic energy of 1 kilo electron volt, and we have to compare this with an X-ray photon of the same energy. So the process is very simple. You can go on calculating. So if I say that the kinetic energy is T is kinetic energy is equal to T, which is equal to P square by 2m. Remember, we want to calculate the momentum, and from there we want to calculate the de Broglie wavelength. So kinetic energy is given as 1 keV, which is equal to 1000 1 keV, 1000 eV, which is equal to 1.6 into 10 to the power minus of 16 joules, because 1 eV is 1.6 10 to the power minus 19 of a joule. So we can calculate the corresponding momentum, E to be equal to 2m into T root over of, from here we can get it. So this would give us root over of 2 times 9.11 10 to the power minus 31 kg, that is the mass of the electron, and then 1.6 into 10 to the power minus 19 joules. So that gives us something like, if you want to calculate it, you can just use a calculator, and then you can evaluate the corresponding momentum to be whatever. I can just give you the right answer, which is lambda is equal to h by p, which is equal to 6.63 10 to the power minus 31 joule second. So this divided by, again, p means kg meter per second, so that gives us a SI unit of meter. If I write this as 2 into 9.11 10 to the power minus 31, and this should be, p is not minus 19 but 16, so this is going to give us 1.6 10 to the power minus 16 whole to the power half, because there is a square root, and that gives us something like point of this would be around if one calculates, then he or she is going to find it as 12.42 angstrom. Okay, so this would be something like 12.42 angstrom. Okay, and then if again one wants to calculate this for an X-ray photon, for this is for an electron, so this was electron case. Okay, and for X-ray photon we have the corresponding energy to be, if the energy is given by E is equal to h nu, which is equal to hc by lambda, and then if we again want to calculate the wavelength from this, hc by E, which is equal to 1.6 into 1 kilo electron volt, same energy. So this would be, so this is again 6.63 10 to the power minus 31, 3 times 10 to the power 8, and divided by E is 1.6 10 to the power minus 16. So This is again in meter, and if one calculates it, then one can very easily find it to be something around oh sorry, this should be equal to 12.42. I am wrong here, and this should be equal to 0.39 angstrom. You can do that in your calculator. You can just use the data and do it in your calculator. So what I need to show is, if an electron is moving with such a high speed, high kinetic energy, which is 1 keV, then it has a wavelength which is much smaller in comparison to the X-ray photon. If one takes the ratio, if I call this as lambda prime, okay, then this lambda prime by lambda, this is the same energy X-ray photon, same energy electron, then the resolution given by an electron is something like 12.42 divided by 0.39, which is of the order of 34.85. That's why we use an electron microscope to view object of much smaller dimension, because it actually gives you a wavelength much smaller in comparison to, and much smaller wavelength are always good for resolution of smaller objects. Okay. So our next problem is regarding an electron scattering experiment, which gives a value of 2 times 10 to the power minus 15 meter as the radius of the nucleus, and we want to have an estimate of the order of energy required to scatter the electrons. So electrons kinetic energy is to be determined by using relativistic expressions. Why are we using relativistic expressions? Because this particular speed or the corresponding energy required is much higher, and that is why we need to have. Where do we use relativistic corrections? That should be made clear, because for charged particles like electrons, the rest energy is of the order of 0.511 MeV. Okay, and if anything is of the order of the rest energy, any energy of the order of rest energy or greater than rest energy, then we need to take into account the relativistic expression. Before that, we need to know the wavelength associated with the moving electron, because de Broglie wavelength. So first of all, let us try to have an idea about the de Broglie wavelength associated with this. So de Broglie wavelength of the electron, how much could be that? To measure a distance of so we know that from diffraction experiment, the resolution 2d sine theta, and sine theta is maximum value is 1, so lambda must be equal to 2 times d. So we can say that this is equal to 2 times 2 into 10 to the minus 15 of a meter. This must be the wavelength associated with the electron wave, which is moving towards the nucleus, to get an estimate towards the nucleus for being scattered by the nucleus, and give us an estimate of the radius, nuclear radii. Okay. So if this is the wavelength, then we know, we have already done this in our Compton scattering, that the relativistic correction is given by the total energy. If the kinetic energy be T, okay, then total energy E is equal to T plus m naught c square, where m naught is the rest energy, c is the speed of the light, and this is basically equal to, according to relativity, is special theory of relativity is p square c square plus m naught square c4. This particular expression has already been used in our Compton experiment, which I have taken as a class, if you remember correctly. We have done this previously. So from here we know that p is, then we can just write it as p square c square is equal to t plus m naught c square whole square, okay, and minus of m naught square c4, and p is equal to 1 by c and t plus m naught c square whole square minus m naught square c4 whole to the power half, and this p can be written as equal to h by lambda by de Broglie relation. Okay. So we can say that h square by lambda square and is equal to 1 by c square and t plus m naught c square whole square minus m naught square c4 is this, and from here we can, the lambda is given by this, so we can invert it to calculate the value of the expression for the kinetic energy, which turns out to be something like, if one wants to, if divided this by, so we can write this by as 1 plus t by m naught c square, okay, whole square. So there is 1 plus t and that is equal to h square, and since you are dividing this, so we can write this to be equal to h square by m naught square c square lambda square, m naught square, there was a c4 and there is a c square, so m naught c square lambda square, and then there is a minus 1, so there would be a plus 1 factor. From here, just putting the value of h, m naught c lambda is 4 times 10 to the power 15, one can get the value of the kinetic energy of the electron to be equal to, this is something like 310 MeV. Okay, in terms of mc square, it is 605.1 m naught c square, which is equal to 310 mega or million electron volts. So that is the answer to the energy of the order of, the energy is of the order of few hundreds of mega electron volt. Okay, this is a problem on an electron having a speed of the order of 500 meter per second with an accuracy of 0.004%. We need to use the uncertainty principle in order to calculate the certainty with which we can locate the position of the electron. So what is the momentum? First we need to calculate the momentum associated with the electron, which is m times v, and the speed is much lower, so we can use non-relativistic expression, which is 9.11 10 to the power minus 31 into 500 kg meter per second, and according to the problem, the accuracy given delta p by p into 100 is equal to 0.004, so that gives us delta p to be of the order of 0.004 into p by 100, which turns out to be 0.004 into 9.11 10 to the power minus 31 into P is okay, 500 divided by 100. So that gives a value of the order of 183.2, I think. 182.2 into 10 to the minus 34. 182.2 into 10 to the minus 34 kg meter per second. Now we want to evaluate if we want to calculate the certainty, we need to know delta x, which is equal to h by delta p, uncertainty relation. Heisenberg uncertainty relation. Okay, so that gives us 6.63 10 to the minus 34 divided by 182.2 10 to the minus 34, which turns out to be around equal to 0.0364 meter. So that's a very straightforward problem. So you can determine the position with an accuracy of the order of 3.64 of an centimeter, and that's the answer. I would like to request you all to do certain problems on quantum mechanics which are given at the end of the third chapter of Arthur Weiser Concept of Modern Physics, Wave Properties of Particles. I would like you to go through the problem of Arthur Weiser chapter 3 and problem 5, and then there was, I think, problem 11 and 12. These are the three problems which were recently given to me by one of my students, and I found that you need to have a better understanding of the first problem. Is all about dealing with the relativistic error calculation, that if you are dealing with a particle moving with high speed and you are trying to calculate the using the relativistic correction, the de Broglie wavelength for relativistic expression of de Broglie wavelength and non-relativistic expression, then you would have different value, because for electron moving with such a high speed, they are going to obviously give you different de Broglie wavelength, and the correct expression is all dealing with relativistic expression. The second problem deals with the fact that if the energy of the particle is much greater than its rest energy, then we can say that the wavelength associated with such particles are the same as that of the photon, because in such cases the energy exceeds the rest energy. And the third problem, problem number 12, deals with an expression of the de Broglie wavelength in the case of relativistic charge particle. Okay, so I would like to see your comments, your feedback, your answers in the WhatsApp group which is being created by our Department of Physics, Vivekananda College, and that would be really encouraging for me. If you want to have more videos like this, please let me know in that particular WhatsApp group. Thank you.